When we look at the universe, we can only see a small fraction of it. Stars, galaxies, and nebulae light up the cosmos, but what about the rest? Dark matter, which makes up most of the universe, doesn't emit light, and it doesn't reflect it either. It's invisible, so how do we search for something we can't see? The search for dark matter began with a mystery. In the 1930s, Swiss astronomer Fritz Zwicky was observing galaxies in the Coma cluster. He realized that the galaxies were moving too fast, faster than the mass of the visible stars could explain. There had to be something else there, something invisible adding mass and gravity. This invisible mass became known as dark matter. It's responsible for providing the extra gravitational pull needed to hold galaxy clusters together. But detecting this invisible force was, and still is, one of science's biggest challenges. So how do we know dark matter is really there if we can't see it? One of the most compelling pieces of evidence is gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravitational pull of dark matter bends the light, creating a lensing effect. By studying how the light bends, we can measure the amount of mass in the galaxy cluster, including the dark matter. This effect has been observed countless times, proving that dark matter is not just a theory, it's a reality, even if we can't see it. But what if we want to detect dark matter directly here on Earth? That's where the most sensitive detectors come in. Buried deep underground in ultra-clean environments shielded from other particles that could interfere. These are direct detection experiments designed to feel the tiny interactions between dark matter particles and regular matter. One of the most famous experiments is the Xenon 1T detector, located deep under the Gran Sasso Mountains in Italy. It uses liquid xenon, a rare gas, to try and detect the incredibly weak signals produced when dark matter particles like WIMPs, weakly interacting massive particles, collide with normal atoms. When a dark matter particle interacts with an atom, it should produce a tiny flash of light, a signal that scientists are hoping to detect. So far, no conclusive evidence has been found, but every experiment brings us closer to understanding this elusive material. Another way scientists search for dark matter is through indirect detection. This involves looking for the particles produced when dark matter interacts with itself. If two dark matter particles collide and annihilate, they could release high-energy particles like gamma rays that we can detect. Some of the best places to search for these signals are the centers of galaxies, where dark matter is thought to be more densely packed. Instruments like the Fermi Gamma Ray Space Telescope are constantly scanning the skies for these telltale signals. Though we've seen hints like unexpected gamma ray emissions from the center of our own galaxy, no definitive dark matter signature has been found. But every year we're refining our techniques and getting closer to a breakthrough. When it comes to dark matter, there are several candidates scientists are focused on. The most popular theory is that dark matter is made of WIMPs, weakly interacting massive particles. WIMPs are thought to interact only through gravity and the weak nuclear force, making them hard to detect. Another possible candidate is the axion, a much lighter and even more elusive particle. Axions could explain some of the strange behaviors we observe in the cosmos, but finding them requires different techniques, such as using powerful magnets to try and convert axions into detectable photons. The Axion Dark Matter Experiment, ADMX, is one such project, using magnetic fields to search for axions and unlock another piece of the dark matter puzzle. While WIMPs and axions are the leading candidates, there are other more exotic ideas out there. Some scientists are exploring whether dark matter could be made up of primordial black holes, tiny black holes formed in the early universe. These tiny black holes could explain some of the gravitational effects we attribute to dark matter. Others suggest that dark matter might be a manifestation of entirely new physics, something we haven't yet discovered. The mystery of dark matter may point us toward a new understanding of the universe's fundamental laws, but one thing is clear: whether it's WIMPs, axions, or something even stranger, solving the mystery of dark matter could revolutionize physics as we know it. So, how do you think we'll detect dark matter? Will it be through direct detection, annihilation signals, or something completely unexpected? Share your thoughts in the comments below. Be sure to like this video and subscribe for more updates on the hunt for dark matter. In the next episode, we'll dive into one of the most fascinating possibilities. Could dark matter be linked to black holes? Don't miss it.